In this episode, you'll see how inequality conditions behave, how their order matters, how to mix them with equality ones, and how a simple change in a parameter value can completely change which row the database needs to access. Hi, I'm Jakub from DB Booster Academy. Let's start with a simple query that selects movies where the budget is greater than $165 million. We also have an index on budget, name, and ID. Now let's see how the database uses this index to find all rows that satisfy the condition. This table shows how the leaf level of the index is organized, sorted by budget, name, and ID. Each row here represents one index entry. This part shows the end of the index. I choose the condition so that it includes all rows that match the condition and a few just before that point. The database uses the index to find the first row where the budget is greater than 165 million. It doesn't need to start from the beginning. It can jump directly to this point in the index. From here, it simply continues scanning forward, reading all the remaining rows that satisfy the condition. Or better said, it scans forward until the end of the index, since our condition has no upper limit. This process is called a range scan or index seek in SQL Server terminology. It's efficient when the engine only reads a small enough part of the index. This works as long as the inequality is on the leading column of the index. But what if we add another inequality on a different column? Now let's make it a bit more interesting. I'll add another inequality, this time on revenue. So we are selecting movies where the budget is greater than 165 million and the revenue is greater than 200 million. I also added revenue as the second column in my index. Let's see how the database can use this index and what changes when we have two inequality conditions instead of one. Here is our index again. This time, the revenue column added right after the budget. The database can still use the first inequality on budget to jump to the starting point in the index. But once it gets there, it can't use the second inequality on revenue to further narrow down the range. That's because revenue is ordered only within a single budget value, not across multiple budget values, as you can see here. For movies with a budget greater than 165 million, the revenues are 205, 199, 91, 241, 227, 176, and so on. So the database has to scan all rows that satisfy the budget condition and check the revenue value for each of them. This means that the revenue acts as a filter predicate. So to sum it up, only one of the inequality conditions can actually narrow the search space. The others can't help. They are applied as a simple filters on the rows that the index already returned. Only the first inequality really drives the index access. The rest just filter the results. Now let's combine an inequality with an equality condition. Our query selects movies where the budget is greater than 165 million and the language is English. We can create the index in two different ways, with budget first and language second, or the language first and budget second. So the question is, where should we place the equality column to make this index work best? Let's start with the first index, budget first, language second. The database can use the inequality on budget to jump to the right starting point in the index. But inside that range, the language column isn't ordered anymore. It contains multiple language values mixed together: French, Chinese, Russia, English, and others. So we use the language condition just as a filter. We scan 13 movies rows with the given budget, but only 7 of them are returned, the ones where the language is English. Now let's switch the order, this time language first and budget second. With this index, the database can locate the first movie in English with a budget high enough. From there, all the following rows are also in English. And for the same language, the budget values are already ordered. So the database can simply read the 7 rows knowing they all match both conditions. We scanned only the rows that meet our criteria, just 7, which makes this approach much more efficient. So, to wrap it up, first, put your equality conditions first in the index. You have to avoid the gap, of course. Second, remember that you can have only one inequality condition used as the access predicate. And finally, all the remaining conditions are just filters applied to the scanned rows. That's the key to building efficient indexes for mixed equality and inequality predicates. Let's talk about what makes a condition good for the index. A good condition is the one accessing the fewest rows, simply making the search space as small as possible. Let's compare a few examples. First, budget greater than 0. That returns all rows, 10,143. Then budget greater than 165 million. Only 13 rows. In this example, you can clearly see how important the parameter value is. The same condition with 2 different parameter values can return a completely different number of rows. In real life, the key question is, how do you get the representative parameter values? Especially if you work as a consultant and know nothing about the system, you have to rely on the customer to tell you. Unfortunately, they often say, make it work for any value, which is rarely possible and total nonsense for inequality conditions. The parameter value is important for equality too, as you will see soon, but for inequalities, it's absolutely crucial. So you can get the value from the customer, or from the business team, or from logs and internal views. But you need solid values to make good decisions. Now, what if we have 2 different columns? Budget greater than 100 million and revenue less than 100 million. We don't know immediately which one is better. When we check, the first condition returns 1,669 rows, and the second one 6,862. So we prefer to start with the one that returns fewer rows, budget greater than 100 million. But again, that depends on the parameter value. If we change it to the budget greater than 0, it would return everything. The amount of accessed or returned rows describes how selective our condition is. Now let's look at equality conditions. The same principles applies here. A good condition is still the one accessing the fewest rows. Let's compare a few examples. Status equals released. That returns 10,120 rows. But status equals banned, that returns only 23 rows. I have only these 2 possible values, so status equals released doesn't help me avoid accessing rows. In fact, it returns almost everything. That means it's not selective, and if I still need to perform a table lookup, this condition doesn't really help, especially considering that status is a character-based value which can also make the index larger. And the same goes for language. Language equals English, that's 7,406 rows. Language equals Czech, just 2. So even with equality conditions, the parameter value makes a huge difference. Some values are very common, others are rare, and those are the ones that make your indexes efficient. The fact that a condition is part of your where clause does not mean it would filter out a single row. You need to consider your condition in the context of other conditions and also consider the parameter values. You should be sure that columns added in the index represent the real value. The conditions narrowing the search space are the best. As you can see, that you can affect which condition is used as access predicate by deordering. But even the filters are useful, especially when you need the table lookup. By filtering some rows on the index level, you can save a lot of time by accessing less table rows. I personally try, if the index is not a covering one, to keep my indexes as small as possible. That means skipping conditions that don't really help, the useless ones. I know that people sometimes tend to include everything from the where clause into the index, but that's a road to hell. Unfortunately, you'd be surprised how often SQL statements contain completely useless conditions. Sometimes it's just a form of protection against unclean or inconsistent data, like budget greater than 0. But in general, useless conditions are common. It's your job to pick the gems, the ones that truly make the query faster. So, let's summarize what we learned about building efficient conditions and indexes. Equality conditions come first. Check the gap trap. One inequality condition following the equality conditions can help us reduce the search space. The rest are just filters, though filters are still important. And remember, parameter values are crucial, and it can be challenging to get realistic, real-life values. So that's it for this episode. Now you know how to decide which conditions really matter, and how the order, the number of inequalities, and the parameter values can completely change performance. In the next episode, we'll take a closer look at order by clause, because it can benefit from indexing too. If you enjoyed this episode, hit subscribe and stay tuned for more deep dives. Thanks for watching, take care, and see you next time.